Alright, so we're going to talk a little bit about magnetic inductance, and there's a couple different varieties. The first one's going to be mutual inductance, and it's basically the property of an electrical device that describes how effective it is at inducing an EMF in another device. And where this is coming from is the idea that you have a moving current that's changing, and it creates a magnetic field, and the magnetic field is changing, and it creates a current in another device or in another, which ends up with the creating an EMF. This is what you'll see in transformers and devices called inductors in a circuit. The symbol for mutual inductance, which is where something is creating the EMF in a different device, is an M, capital M, and the unit for inductance in general is a Henry. So mutual inductance, you can see that we've got two different coils. You've got a coil with a current in it, and it's created a magnetic field, and the moving charges created the field. And then some of that field goes into the second coil and creates a current in the second coil, which leads to the EMF. And the equation for it, you can see, is right here. So mutual inductance is the number of turns in one of the coils times the flux divided by the current in the coil. And that phi21 or phi12 is the flux. And so if we look at phi12, that is going to be the flux in coil 1 due to coil 2. If you take Faraday's law and you combine that with the idea that the total flux in a coil is the number of turns times the flux through one coil, you can find the EMF in that coil. And so you go through and work it, so you get the EMF in the second coil is the derivative with respect to time of n times phi, and then that is the mutual inductance times the current, and the mutual inductance is going to be a constant, so it comes out, and you end up with just the mutual inductance times the changing current with time. So another kind of inductance is self-inductance, and it's the measure of how well a circuit or circuit element can oppose the magnetic flux produced by the circuit. So a circuit has a current flowing in it, and if you have a changing current, you're going to create a magnetic field, and the changing magnetic field is going to induce an EMF in that circuit or in that circuit element, and then that induced EMF is going to create a current that will create a magnetic field that opposes the flux. So self-inductance is basically the ratio of magnetic flux to the current in the circuit. And so any circuit or any conductor can have self-inductance. It can be a coaxial cable. It can be just a single loop of wire with elements attached to it. Self-inductance is abbreviated with a capital L, and it is also measured in henries. So when we talked about self-inductance, there was the induced EMF. And so inductance is the ratio of the magnetic flux to the current. And so if we want to find the EMF, you take the derivative of the flux and do some substituting using Faraday's law, and you end up with an expression for the induced EMF. So inductors store energy in the magnetic field, and it works similar to capacitors. Capacitors are storing energy in the electric field. This is storing energy in the magnetic field, and the model is similar. And so we can use that idea and the idea of magnetic energy density to come up with an expression for the energy that's stored in the magnetic field. U is the energy, and it is 1/2 times the inductance times the current squared. And so looking at the specific example of a solenoid, which would be a coil, usually tightly wound, not like my picture there, with a current flowing in it, has a radius and some length L. You can start with Ampere's law and the idea that the flux is the magnetic field times the number of turns times the area. and then substitute that into the expression for inductance, and you're going to end up with an inductance that's in terms of the area of the solenoid. So current's gone, so it's just about the geometry of the solenoid. So here's an example where you calculate the self-inductance of a solenoid, and it had a little bit of a twist to it. You had to figure out how many turns were in the solenoid, so it gave you the diameter of the wire, or you could find the diameter of the wire, and it told you how long it was. So you kind of had to figure out how many wraps of wire would fit in that length, and so you end up with 400 turns. The other twist to this was the area was given in square centimeters, so you have to make sure you make the change to square meters, and then you just plug it into the equation and do a little bit of algebra. All right, and so if we want to take this one step further and find out what's the induced EMF in the solenoid between the ends of it is how it would be worded. We're going to have the current decrease from 10 amps to 0 amps, so we do have a change in current. So we will have that induced EMF, and we have a time. So that gives us the change in current over change in time, and we have the inductance from the previous part of the problem. You just plug that in, and you end up with 4.5 times 10 to the minus 3 volts. I hope this gives you a little bit of help understanding some of the things about inductance. Remember, you've got to have a changing current, changes the magnetic field, changing magnetic field creates a current, which creates an EMF, and it's all due to the geometries. So good luck.